we're going to talk about duality in what I'm calling general programs. That's not really a distinction that we usually make when we talk about duality, but since we talked about duality in linear programs last time as a special case, we're just using this phrase to refer to the fact that we're going to go beyond linear programs today, using a concept called Lagrange duality that we saw last time. Before we start with that, just was going to say that homework 3 has been released this morning. You guys have 2 weeks to do it. I think a lot of people ran into the fact that this last homework that they found the coding part more challenging than they expected. Make sure that you look at the coding exercise, especially on the homeworks early, and download the files, unzip them, look at them, and make sure to come to us early if you have questions, because my office hours aren't really very crowded. I get probably one person each week, and if you guys are having trouble, I'm more than happy to help, and so are the TAs. So make sure that you start the homework early. This assignment, by the way, this next assignment, is not going to be super challenging in terms of the programming exercise, because this assignment is covering the theoretical unit we're on now, mostly, which is KKT conditions and duality. So it's mostly to do with kind of the theoretical exercises behind those two, but there is a coding part like there is for every assignment. So take a look at that. It's due from 2 weeks from yesterday. Any questions before we plunge ahead with duality? Okay. So last time, just to remind you what we looked at duality in linear programs. And so I wrote the linear program in this form. Minimize some linear function C transpose x subject to linear inequality and equality constraints ax equals b and gx less than or equal to h. In the context of duality, we call this the primal linear program. This was the original linear program we were interested in. And we derived what we call the dual linear program, which was a maximization problem. It was also a linear program. That was one of the properties we saw of LPs, that their duals were also LPs. And last time we really only studied LPs. And how do we arrive at this dual linear program? Well, we had the following explanation, which is that if I defined a variable, which we called the dual variable u, over these constraints, the equality constraints, and if there was m equality constraints, right, if A had m rows, and this was like ai transpose x equals bi, for I going from 1 through m, we defined a dual variable ui for each of those equalities. So u is m-dimensional. And likewise, we defined a dual variable vi for each of these r inequalities. And we put the constraint that each component of v had to be non-negative. Because we're going to take each component of u and multiply it by the corresponding equality, each component of v and multiply it by the corresponding inequality, and we restricted vi to be non-negative so that it doesn't flip the sign of this inequality. That's why we had that constraint. And we had this idea that if we did that, then if we took, say, the sum of the products of those dual variables with ax minus b, and of the dual variables v with gx minus h, then that's always less than or equal to 0. Because if x was feasible, then ax is equal to b, so this part's 0. Gx is component-wise less than or equal to h, so this part is less than or equal to 0. And therefore, for any u and for any v that has non-negative components, if you add these two things up, it's going to be less than or equal to 0. So we were generating new constraints. We were generating new linear constraints by taking linear combinations of existing constraints. Constraint generation, that's how we thought of it. And what we did is we tried to rearrange this quantity so that we had something that looked like C transpose x is bigger than or equal to something else. And we said that if we could make the leading term multiplying x be equal to C, then that would serve as a lower bound on the optimal value of this criterion. Right? Because if this is true for any feasible x, then at the solution it certainly has to be true as well. So we said that if we could make A minus A transpose U minus G transpose V equal to C, which we do in this constraint, and if we restrict V to be non-negative, then this guy serves as a lower bound on the primal criterion. And to get the tightest lower bound possible, we're going to maximize over all such u and v, all choices of u and v, and that's how we formed this dual linear program. Okay, any questions about that? That was what we did last time. Okay, what we saw immediately was that this was useful in the sense that we saw an example of how this came into play with max flow and min cut. It was pretty interesting. We saw that in that example and in other examples, we convinced ourselves that often we get a tight lower bound in the sense that the optimum value of this dual LP is equal to the optimum value of this prime LP. And when I polled the class, you guys thought that pretty much would always happen, which was good intuition. It pretty much does always happen. And we'll learn that today precisely. So this is a nice way of constructing dual programs in the LP setting. It's limited, though, because if you think about it, if I had linear constraints and I was just generating new constraints, I can't really ever get a lower bound on a criterion that's not linear, conceptually, with this method. So if I asked you to minimize a quadratic function subject to linear constraints, you could generate all new constraints, to your heart's content by taking combinations of these constraints with dual variables, but that you wouldn't be able to express that combination as a quadratic in X. So conceptually, this was limited, although for linear programs, it's very concrete, and so it's nice. So to move towards general programs, right, where we're minimizing a function subject to a function being less than or equal to 0 and a function being equal to 0, right, a kind of generic optimization program, we looked at a different perspective, which is called Lagrange duality. That's the second explanation. And in the case of linear programs, it exactly coincides with what we already learned. So there's no difference between considering the Lagrange dual or this particular type of dual we got from constraint generation. And here's the second explanation. We'll form dual variables u and v as before, and we'll look at what all u and v that's non-negative in each component and primal feasible x. And we'll say that the primal criterion, C transpose x, is always bigger than or equal to C transpose x plus U transpose AX minus B plus V transpose GX minus H. Because by the same logic as before, if x is feasible, this part 0, and this part is less than or equal to 0 in each component. So if we form this linear combination, it's always less than or equal to 0. So I can always add that to C transpose x, and it only ever brings down the criterion. And we defined this thing to be what we called Lagrangian, which is a function of three variables: the primal variable x and the dual variable u and v. And now we know that if C denotes the primal feasible set, so it's the set of all x for which those constraints are met, for which ax equals b and gx less than or equal to h, then for any combination of valid dual variables, if I minimize C transpose x over the set C, I get f star by definition. That's the primal optimal criterion value. Just from this inequality, we know that that's going to be bigger than or equal to minimizing the Lagrangian over the set over x and being in C. Because for every x, we have C transpose x is bigger than or equal to L of x u v. So if we minimize over C, the same inequality is going to hold. And now we further relax this by saying, let's consider minimizing the Lagrangian not only over the constraint set C, but over all x. That's still going to be a lower bound on f star, because if I remove the constraint that x had to be in C, I could have only made this quantity smaller. Right? I'm making the domain of the minimization larger. And that we define as a new function g of uv. So that doesn't depend on x, right? Because we've minimized out x completely. That's called the Lagrange dual function. And so what we've said is that for any valid dual u and v, we get a lower bound on our primal criterion at optimality, f star, with this function, g of uv. It's called the Lagrange dual function. If you went through the calculation, right, if we tried to minimize this over all x unconstrained, then we'd see that we'd get a function that looks like either this part, minus b transpose u minus h transpose x. That's all the terms here that don't involve x, as long as c was equal to minus a transpose u minus g transpose v, because then all the terms up here involving x cancel out. Or it's minus infinity, because if there's any term left involving x that's not canceled out, we can always make that linear function as small as we want. So that was our dual function. And maximizing this dual function, which gives us the tightest lower bound possible, maximizing this GUV, you can see, is exactly the same as this dual linear program. So the construction from Lagrange duality exactly coincides with what we did before. But we like it because it's actually completely generic. It doesn't depend on linearity. You can imagine if we had just arbitrary functions here, the same arguments would go through, and that's what we're going to cover today. So let's jump ahead and do that unless there's any questions. So today we're going to talk about the Lagrange dual function, the Lagrange dual problem, weak and strong duality, some examples of dual programs, and then we're going to give a preview of the uses of duality. So we'll come back to that in a couple lectures. We'll talk about how dual programs are used and why the concepts of duality are very useful. We'll just give a preview today. So the first two parts, on the Lagrange dual function and the Lagrange dual problem, we've pretty much already covered it, although we just talked about it for linear programs. So there's really not much new you're going to learn here. Conceptually, we're just going to change all of the linear functions we saw to arbitrary convex functions. And I said this before last time, duality in the KKT conditions, this unit involves very simple arguments. There's nothing complex here mathematically. Nothing as complex as, say, deriving the prox function for the trace norm or other things we've done in previous lectures that was more complex. They're very, very simple arguments, but they're subtle. So it's kind of easy to, I think it's easy to get lost in how subtle they are. So we're going to consider a general minimization problem. And we've seen this before, although at this point I'm not even going to restrict this minimization problem to being convex. So I'm just going to say that we're going to minimize some function f subject to a bunch of inequality and equality constraints, hi of x less than or equal to 0, lj of x is equal to 0 for a bunch of I and j. We're not going to restrict f and hi to be convex and lj to be affine. So at this point, we're not actually going to consider this necessarily a convex problem. Of course, we're going to pay special attention to that case, but duality is very powerful. Despite the fact that it's very simple in terms of the conceptual construction, it's very powerful and it can be applied to non-convex programs as well. So we're going to define the Lagrangian, just like we did with linear programs, to be the following quantity. It's a function of three variables, the primal variable x, and dual variables u and v that we construct that correspond to these constraints. We're going to construct here I called ui, the dual variable corresponding to this inequality constraint for all I, and vj, the dual variable corresponding to this equality constraint for all j. Now we're going to constrain, just like we had before, ui to be non-negative for each I, because we don't want to flip the sign of this constraint. The Lagrangian is just defined by taking the criterion function and then taking linear combinations of those dual variables and the constraints. So we're going to add the sum of ui hi of x over all I and add the sum of vj times lj of x for all j. Okay, so this Lagrangian, like I said, is a function of three variables. The domain of the Lagrangian over the dual variables, like we said, is implicitly, we're just considering u to be non-negative in each component. So this is an important property, which, like I said, we just saw for linearity, but it's true in general, which is that if you give me any valid dual combination, u and v, dual pair, and any feasible x, then the Lagrangian lower bounds the primal criterion. F of x is bigger than or equal to L of x uv. Why? For very simple reasons. If we just look at L of x uv, then we're taking the criterion, f of x, and we're adding to it two things that are both non-negative. Non-positive, both less than or equal to 0. Because if I take ui times hi of x, then because x is feasible, hi of x is less than or equal to 0, and ui is bigger than or equal to 0, so this product is less than or equal to 0. So I'm summing up a bunch of things that are all less than or equal to 0. The result is something less than or equal to 0. Similarly, for a feasible point, lj of x is equal to 0. So this term is always equal to 0 no matter what vj is, and that's true when I sum it up as well. Okay, so that's just less than or equal to f of x for a very simple reason. So here's a picture of what the Lagrangian, say, looks like. the solid line in this case is f. It's not, you can see, it's not a convex function. And the feasible set is essentially everything in between these two dashed lines. Okay, so we're trying to look at, say, f subject to x lying in between about minus 0.5 and 0.5. Then what we're showing here in all of these dotted lines are one of these Lagrangian functions as a function of x for a given pair u and v. So I'm just picking a certain pair u and v. See if I can zoom in so you get a better idea of the picture. Each one of these dotted lines, we pick a pair u and v. In this case, there are no equality constraints, so there's just an inequality constraint. And I have to have the property that the v corresponding to those two inequality constraints has the right sign. There's two of them because I'm constraining myself to being in an interval. So I just pick some v with the right sign, or I guess u with the right sign here. That's what we're calling the Lagrange multiplier for the inequality constraints. And I'm evaluating the Lagrangian for that fixed dual variable. And you can see it does indeed lower bound the criterion function, which is the solid line, no matter what I choose. Okay, so this is just demonstrating that fact with this particular example. Nothing to do with convexity here, nothing special. It's just via a very simple construction that we get a lower bound on the primal criterion. Okay, so now we're going to define the Lagrange dual function just like we did before for linear functions, which was just gotten by minimizing the Lagrangian over all x. So if we take the Lagrangian and we minimize it over all x, not just feasible x, but all x, unconstrained, and that gives us what we call the Lagrange dual function, which is only a function now of u and v, the dual variables. And because f star, right, f star was equal to the minimum over all feasible x, that's we're denoting feasible x by the set C of f of x, and f of x was pointwise bigger than or equal to the Lagrangian. Right, this was true for every x, as long as u and v were valid dual variables, or what we're going to call feasible dual variables. Then we have this inequality, and we're going to further relax the minimization to be over all x unconstrained. It gives us only something that can be smaller, because we've made the domain of minimization bigger, and that's defined to be the Lagrange dual function. Okay, so for any feasible u and v, the function guv is smaller than or equal to the optimal primal value by construction. Again, just from this simple construction of dual variables multiplying constraints. So from this last, I think this is last. Yeah, from this last picture, I think, now we're showing the optimal primal value, which is f star, and we're plotting here the dual function, which is just a function of one variable in this case. So I guess this must not be the same example, because we only have one dual variable, whereas before we would have two. So here's just an example where we have one dual variable. We're calling it lambda, but you can think of it as our u. The primal optimal value is f star, and I'm plotting here the dual function as a function of the dual variable. You can see that for any feasible dual variable, in this case, it's just constrained to be positive. Suppose it was multiplying an inequality constraint. So for any lambda that's bigger than or equal to 0, this provides a lower bound on the optimal primal criterion value. Right? G of lambda is less than or equal to f star for all lambda bigger than or equal to 0. Demonstrating that this fact that we just derived. Jersey, yeah?
In the equation on that slide, for the inequalities to hold, you have to have u greater than or equal to 0. Right? That should be.
Yes. Right, so I think that's written down below, but you're right, yeah. So it's true, this is only true, it's an important point, for what we're going to call dual feasible U and V, which means that U has to be component-wise bigger than or equal to 0. An important point. Okay, so there's something curious about this picture, right? Suppose we were doing this in an example we cared about, we would have constructed the dual function, suppose it looked like this. We would have said to get the tightest lower bound possible, what am I going to do? I'll maximize g of lambda, overall lambda bigger than or equal to 0. If we wanted to seek the tightest lower bound on the primal criterion value that we could find, what would that be? That'd be something around here. We take, the dual variable, it looks like around 0.6 or slightly less than that. Doesn't equal the primal optimal value here, right? So there's a gap between the optimal primal and dual values. So that's something that we'll see kind of rarely happens in the problems we care about if we're talking about convex problems, but can happen quite often for non-convex problems. So here's an example just to get ourselves kind of grounded. Let's try to derive the Lagrange dual function for a quadratic. Okay, so the QP looks like this. Minimize over all x. Some quadratic function subject to ax equals b, and x being bigger than or equal to 0. And we're going to say that q is positive definite. So just a refresher, what does that mean about this problem if I tell you q is positive definite? It's strictly convex, right? So it's convex, it's actually strictly convex. So what does that mean about its solution? It's a unique solution. Okay, that's good just to refresh our memories. So what we saw for LPs was that the dual of an LP, or the dual function of an LP was also linear. We're going to see if the same thing holds for a quadratic. So let's form the Lagrangian. It's the first step, which we just get by taking, we're going to call U the dual variable for that set of inequalities, and V the dual variable for this set of equalities. I'm going to rewrite this so that it looks like minus x is less than or equal to 0, just so it matches our canonical form. And L of xuv is equal to the quadratic, which is our criterion, plus, so it's going to be plus u transpose minus x, right? Because I'm taking the sum of ui times minus xi. So let's write that as minus u transpose x. And the sum of vi times each of these equality constraints, ai transpose x minus bi is equal to 0, which I can just write as v transpose ax minus b. And now I'm going to try to say that suppose, right, v was anything and u was something that was bigger than or equal to 0, each component, then the Lagrange dual function I get by minimizing this over all x. So let's rewrite that so that we can figure out how to do that. Let's rewrite this as itself a quadratic. We can see this, that if I only look at this as a function of x and think of u and v as fixed for this minimization, it's still a quadratic. So what's the quadratic term? It's still just x transpose qx. And what does the linear term look like? It looks like c minus u plus a transpose v transpose x. And then the only part that's left over is minus b transpose v. Okay? And what's the minimizer, first of all, of this quadratic? What value of x is this minimized? So this is how you guys should always remember minimization rules for quadratics, because you'll see them essentially over and over and over again. If I just gave you a one-dimensional quadratic, so if I give you ax squared plus bx plus c, what's the minimizer of that? Minimized at x equals minus b over 2a. So what is it for this? It's the same rule, but that's b. A is a matrix, so instead of dividing by 2a, we'll just take a inverse. So it's minus whatever this is, which is b. So it's going to be minus c minus u plus a transpose v over 2 times a, but a is a matrix, so it's actually going to be q inverse times this. And there was a half here, so that multiplying by 2 didn't do anything. So that's the minimizer. Minus q inverse c minus u plus a transpose v. Plug that in, what do we get? So then we get g of uv is equal to, we're going to have essentially minus 1/2, or in this case it's plus 1/2 c minus u plus a transpose v transpose q inverse transpose itself. We get minus 1/2 that same, minus 1 times that same quantity from here, and b transpose v. So it ends up just looking like minus 1/2 c minus u plus a transpose v transpose q inverse times itself minus b transpose v. And so that's the Lagrange dual function associated with this problem. And so what we know is that if I took u to be non-negative in each component and v to be anything, then this function is less than or equal to the optimal value of this problem. Right? Pretty non-trivial if somebody just gave you that and asked you whether that was true, but it's very simple as to how we constructed that and why that's true. So how would we get the best lower bound possible, by the way? What would we do here? We'd maximize this overall u that's non-negative and v being unconstrained. And so that would be another quadratic program, right? Maximizing a negative quadratic, same thing as minimizing a quadratic. In fact, it's also convex, right? So the dual of this QP is also a convex QP. Now you can see why it was important for Q to be positive definite. I want it to be invertible. If it wasn't invertible, then the calculation can still be done. That's on the next slide. The dual still exists. It just has more constraints, essentially, and we replace the inverse by the pseudo-inverse. And if you guys don't remember what that is, take a look at some of the linear algebra review notes that Nicole posted at the start of the class. Okay, so I won't go through this calculation, but you can go through it if you're interested. This is the case when Q is still positive, semi-definite, but not necessarily positive definite. Any questions about this example before we move on? Or about duality in general? Yeah?
So we didn't really solve the problem yet by forming the different function, the Lagrange dual function. We didn't solve the problem. We just transformed it into probably an easier problem.
It's a very valid concern or question. Yeah, at this point, I haven't told you the solution to this problem. So I'm not claiming duality gives us the solution, but we're going to see when we talk about uses of duality that yes, it often gives us a problem with complementary structure. I wouldn't say always easier, but sometimes easier, always kind of with complementary structure. So it's often something that we want to look at. It can be easier in many situations, and we'll talk about how you can think of those. Well, so here's a very basic notion. We talked about this last time. How many variables does the dual problem have? Number of constraints, right. So let's suppose I had a quadratic program in 1,000 dimensions with 5 constraints. Its dual problem is going to have it's going to be a problem in 5 variables. Right? So in that sense, its structure is complementary, kind of switches the roles of the constraints and the dimension, and so it might be cheaper to solve the dual in that case. But we'll talk about that in detail. It's a very good question. We'll talk about that in detail, kind of starting at the end of this lecture, and then we'll have a whole lecture on uses of duality coming up. Other questions? Okay, here's another example of a quadratic program in 2 dimensions. And I'm just trying to visualize this relationship for you. The fact that, the primal is a quadratic, the dual is also quadratic. This quadratic always lower bounds that one. So we just derived. I'm doing it in 2 dimensions to give you an idea of that. So x is 2-dimensional. I have no equality constraints, and I only have the constraint that x has to be bigger than or equal to 0 in every component. And there's 2 components, so what's the dimension of the dual variable here then? It's also 2, right? Because I only have 2 constraints. x1 bigger than or equal to 0 and x2 bigger than or equal to 0. So I have two dual variables, u1 and u2. So I did that on purpose so that I could put them on the same graph, just to help visualize them. So here's the primal quadratic surface that I'm trying to minimize, subject to x being bigger than or equal to 0. This is f of x subject to x being bigger than or equal to 0. I've drawn its minimizer as a red dot, and I've drawn a line through it so you can see the value of the primal function at optimality. Here's the dual quadratic that we get from this construction. So I just went through this. I went through this exercise with the simple case when a was nothing, it was 0, and we were in 2 dimensions. And I got this quadratic surface. Sure enough, over the feasible set, right, when u is bigger than or equal to 0 in each component, I get that the dual surface is a lower bound on the primal surface. Right? You can imagine that that may not happen outside of the feasible set. When I don't take feasible dual points, that may not happen. But here's the Lagrange dual function. It's only a function of u1, u2 over the feasible set of the dual. It lower bounds the primal surface. And I've now looked at the largest value of the dual over this surface. I've done that in blue. So that's the maximizer of the dual surface. So this is the tightest lower bound we can get from the dual QP. And it matches the primal optimal value in this example. So this is an example where actually the dual and primal problems have equal optimal values, and there's not a gap between the 2 of them. So what else do you notice here about this blue point? It's hard to tell from this perspective plot, but I'll just tell you that this red point lies inside the feasible region. So it's at a point where both x1 and x2 are strictly positive. Look at the dual optimal point, the maximizer of the dual program. It's at a point where both u1 and u2 are 0. Is that a coincidence? Can somebody predict why that happened if they've seen something like optimality before? This is a preview of what happens. Okay, yeah, I wouldn't have expected maybe many people to have caught this, but that's something called complementary slackness. We're going to see that that's an implied condition that comes from the KKT conditions. So we'll learn that next time. I just was curious to see if people had intuition for that. So that's the start of a relationship we're going to describe in much more detail next time between the actual dual and primal solutions. Now we're just talking about their optimal values. Next time we'll get at the relationship between the primal and dual solutions. Okay, so we've been going through this game kind of in the exercises of maximizing the dual program to get the tightest lower bound. Here's just formally what that looks like. Maximizing the dual function, to get the tightest lower bound. Formally what that looks like is just to take the constructed function GUV and maximize it overall feasible U and V, which just means that U has to be bigger than or equal to 0. This gives what we call the Lagrange dual problem. By construction, right, this is always going to be less than or equal to f star. GUV is always less than or equal to f star for any feasible dual pair. So if I maximize overall feasible dual pairs, it's still going to be less than or equal to f star. Let's call the maximum value of this program G star. So we've just established what we call weak duality. What is that? If you have the optimal value of this program and this program, the primal and the dual, and you call those F star and G star, then it's always true that F star is bigger than or equal to G star. There's nothing about convexity here. That's always the case. We always get a property called weak duality. So if all we're looking for is a proper lower bound, we can get it with the dual problem. Here's another kind of fascinating property that I think people are often surprised by when they see. I claim the dual problem is always a convex optimization problem. So as I've written it, it's a concave maximization problem. Right? If we maximize a concave function, we know that's equivalent to minimizing a convex function. So we still call it convex optimization. We talked about that at the start. It's just notation. So I claim that the dual program is always convex, regardless of whether the primal is convex or not. And this really, I think, surprises people when they see it for the first time. So you can write down the most horrendously complicated non-convex problem you want, and if you could derive its dual, it would be convex, a convex optimization problem. And as written, you'd be maximizing a concave function. And you'd still get a valid lower bound. Why is that true? Well, it comes from some very simple composition rules for convexity, like we learned at the start. It's just written up here on the slide. By definition, the dual function is the minimizer over all x of the Lagrangian, right? F of x plus the sum of ui hi of x plus the sum of vj lj of x. And I'm going to rewrite this by saying this is minus the maximum of the minus Lagrangian, the negative Lagrangian. I didn't do anything, just wanted to flip it around that way. Let's look at this maximization as over x with u and v considered fixed. What kind of function is this? For fixed x as a function of u and v, what kind of function is this? Let's write down here it's maximum of f of x So let's just call this function L sub x of uv. What kind of function is L for a fixed x? It's just an affine function, right? That's all it is. The appearances of u and v just appear in these sums. So this is affine for each x. And hence it's convex for each x, right? Convex functions are always, affine functions are always convex. So now I'm telling you that I'm going to maximize over a bunch of x, L of x uv. And I'm going to call this function something else. What is this as a function of u and v? Pointwise maximum of convex functions is convex. That trick we've learned several times and used several times. And this is just equal to minus GUV as we've written it, right? Hence, GUV is concave. And if you look at the constraints, all I'm doing is I'm constraining the dual variable to be non-negative, u. So those are convex constraints. Therefore, the dual problem is always maximizing a concave function subject to convex constraints. Questions about that? It's the start of one of a few surprising facts about duality. Okay, this exercise I remember I did in a previous course just to prove the point, but it took me a long time to go through, so I'm going to skip it this time. But I'll probably post the details in some way or another to the notes. It's an interesting example of this fact. And what I did is I took this quartic function, it's a univariate quartic function, x to the power of 4 minus 50x squared plus 100x. It's non-convex, not a convex function. I've drawn it here, so you can look at what it looks like here. And I've laid down the constraint that x must be bigger than or equal to minus 4.5. So I'm considering the problem of minimizing f of x subject to this constraint. I've went ahead and I've derived its dual. So I derived the dual function. And the reason I picked a quartic function is because I could use some of the closed form expressions for the roots of a cubic equation. So I took its derivative. I set it equal to 0. I found all of its stationary points, which I could do because the derivative of this function is a cubic. And then I've looked for which of those stationary points gives me its minimizer. Once I've added in minus 4.5 times u into f. And I've actually explicitly formed its dual function. It's horrendously complicated. It's an extremely complicated expression with, if I'm remembering correctly, it has fractional powers in both the numerator and denominators. So it's a very, very complicated function, the dual function. And if I gave that to you guys and asked you on first principles, is this a convex function? This is an example where your rules wouldn't help you. It would be very, very hard to spot that thing was convex. And maybe if you worked at it for a really long time, you'd be able to see kind of some of the structure. But at least when I remember looking at it, it was a very, very complicated function. Not obvious that it's concave, actually. I was saying convex, but actually it's concave. But we know from this previous fact, right, that it must be concave. So it's a pretty interesting case where it's such a complicated function that it's hard to tell in any other way. And you might encounter this in some of your problems. If the dual function ends up looking quite complicated, we know it's always concave. So in a sense, we always have nice properties when we use it. And here's another case where I've plotted the dual function as a function of the dual variable v. I've tried to maximize it to give the tightest lower bound possible. And you can see it gives us a gap on the primal criterion value. So here's a case where the primal optimal value and the dual optimal value are not the same. So we have weak duality always because the red line's always bigger than or equal to the maximum of the black line, but we don't have strong duality, they're not equal. So in the examples we've seen so far, by the way, we've seen examples where we have a duality gap and examples where we haven't had a duality gap. What's the common denominator there? It seems to be convexity, right? It seems like the convex examples we've looked at, we've had the dual and primal problems matching in optimality. The non-convex ones we've looked at, we've missed that. Yeah?
Just to be clear, so when you said G is concave in U and V, it's only concave in the domain where U is positive, right?
Correct.
So strictly speaking, it's a convex optimization problem. The dual problem is a convex optimization problem, but it would be wrong to say that G is a convex function.
Yeah, G is a concave function, but we define its domain to be the set of all U for which U is positive and V is anything. And outside of that, we define it to be, say, minus infinity. So that function is concave. It's a good question. OK, let's take a break, and you can soak some of these concepts in, and then we'll come back and we'll do a few more examples. Let's pick back up. So we actually don't have, if we get through all the rest of the duality material, which there's not much more, we may go back and do the minimax matrix games example, just because that one's a fun one that we didn't get to last time. So we'll just see how much time we have at the end. So we always have this property called weak duality, which means that the primal criterion is always lower bounded by the dual criterion at optimality. And I wanted to just say kind of a bit of a caveat, which was that it seems like this concept of duality is it's very powerful because when we derive a problem's dual, it's a convex problem. And so it seems like somehow we've taken a very hard non-convex problem and gotten a convex one out of it. But there's two important caveats there. The first is that it's not always easy to explicitly derive duals. So if you could form this maximization, the minimization of the Lagrangian, then whatever that function is, it is going to be concave over its domain. But that's not always easy to do. It's not always easy to write down what the dual function will be analytically. That's actually true for convex problems even. It's often not very easy to derive the dual function explicitly. It takes some work. There are some tricks, as like we'll see, involving what we call conjugate functions. But it's not always easy. It's not always possible. For non-convex problems, that's even more true. So generically, it's a lot harder to derive the dual function in closed form for a non-convex problem. So that's a major roadblock to actually even going to the dual. It's just getting an analytic expression for it. Furthermore, even if we could get the dual function, depending on what our goal is, we've already seen examples that with non-convex problems, say, there may be a gap between what we can get with the dual and what we can get with the primal. Right? The dual actually may be strictly smaller than the primal. And that's kind of generically true for non-convex problems. There are many exceptions, but we don't have kind of broad rules for non-convex problems that tell us when we get those two matching. So there's a big caveat there. The dual is a convex optimization problem, but it's not one that's going to fix all of your needs. It's not going to solve all your needs for non-convex optimization. So let's get back to this concept of when there is a gap and when there's not. Seems like that's been a question we've had in our minds for a while now, the last couple of lectures. We always have weak duality, but in convex problems we have observed in many instances that we actually have strong duality. So F star and G star are equal. And there's a very general condition under which that's true, and it's called Slater's condition. And it says the following. If the primal problem is convex, we know what that means. F is convex. Inequality constraints are convex. Equality constraints are affine. And there exists at least one strictly feasible x. So there's at least one x that satisfies all of the inequality constraints strictly and all of the equality constraints, right, just period. So there's not a notion of strict satisfying an equality constraint strictly. Then we get strong duality. It's very, very general, and pretty much any convex problem that you would want to look at is going to satisfy Slater's condition, right? It's not saying this has to happen at the solution, and in fact, a lot of times it won't happen. This won't happen at the solution, but it's just saying that there has to be a feasible x for which this is true. So, in some sense, the constraint set that you're writing down can't be trivial in some sense. There's an even weaker version of Slater's condition, which says that we only require strict inequalities over the non-affine inequality constraints. So if these are affine, if Hj or Hi happens to be affine, then we don't require there to exist an x such that Hi of x is strictly less than 0, along with all the other constraints. We can just make that less than or equal to 0. So that's the kind of weakest version of Slater's condition that we know. Pretty much holds, like I said, for any primal convex problem.
Yeah, any intuition on why the strict inequality is needed?
For the non-affine?
Yeah.
It's a good question. So the way that Slater's condition is proved is usually geometrically. So there's one usually turns to kind of a geometric construction. I'm not sure if I can give good intuition for why we need strict inequalities. It has to do with that constraint not being kind of active. I'd have to think about it.
Any known examples where inequality is feasible or not strictly feasible and where it is not hold?
Where Slater's condition does not hold?
No, so are there any conditions where there exists only feasible solutions but not strictly feasible solutions, and strong where it is not hold? So for instance, I'm giving you a solution that's feasible in the sense that inequalities can be satisfied but not strict.
Oh, and you want to know that strong duality still holds?
And strong where it not holds.
Oh, so you're asking if there's a converse to Slater's condition?
Right, yeah.
I don't know, actually. So we could consult Rockefeller. That would be the reference I would look to find this out. I think Slater's condition might have a partial converse. Do you know, Javier?
So, if I understood I'm not sure that I'm understanding the question exactly, but when the Slater condition fails, there could be a duality gap.
Right.
Okay, now, it could be that the condition fails, and still there is no duality gap. there's no reason, there's nothing like any kind of.
Yeah.
With regard to the intuition, it's not simple. One way of getting some intuition is that one way of proving duality is via something called the theorem of the alternative. Then the strict inequalities just allow you to apply the proper alternative to then get
Right.
But you know, it's not something. It's not a straightforward intuition for why that implies duality.
It's a good question. So we're going to see an example where we don't have Slater's condition holding next. You'll see one. And you'll actually see there is a duality gap in that case. So we'll go to LPs, back to where we started. We're going to try to figure out when we get strong duality for LPs. The answer is essentially always, unless you write down a very bizarre LP, which I doubt you'll encounter in practice. But you may. So, okay, how do we figure that out? Well, if we write down the dual LP, it's easy to check that if we take the dual of that, we get back the original LP. So we can't kind of generate duals in some unlimited sense. The dual of the dual is the primal. And if you're curious as to when that happens, I think we'll talk about that in a next lecture or lecture after that. It's also kind of a general principle. So the dual of the dual LP is the primal. Go ahead and check that. Just derive the dual of the dual if you're curious. And let's now use the refined version of Slater's condition, which says that we have to have the problem just being feasible in order to get strong duality. Right? Because we don't need anything to be strictly satisfied. With an LP, all of the inequality constraints are affine, so all we need for the weak version of Slater's condition is that there is a feasible point, since it's always a convex problem. So let's apply it to the primal problem. If the primal LP is feasible, we get strong duality, so F star and G star are equal. Let's apply the same logic to the dual. If the dual problem is feasible, we get strong duality between its optimal value and its dual's optimal value. But its dual is the primal. So Slater's condition implies, when you apply it both to the primal and the dual, that if the primal is feasible, you get strong duality. If the dual is feasible, you get strong duality. When's the only time you don't get strong duality? If both the primal and the dual are infeasible. Then Slater's condition doesn't tell us anything, doesn't hold. In that case, you can actually check that you do get a duality gap. Right? What's the duality gap in that case? If the primal is infeasible, what's the primal optimal value? And if the dual is infeasible, what's the dual optimal value? Minus infinity. So that's the biggest duality gap possible. But if either of them are feasible, you get strong duality. Okay, so like I said, pretty much always with linear programs, strong duality holds. Let's go to an example which I think you probably have seen before if you've taken 701 or 601 or countless other ML courses. It seems to be a very popular dual, so as far as ML problems go, is the support vector machine dual. And it's not very hard to construct, so let's go through that now as more practice with deriving duals. So to remind you, right, the support vector machine problem, I have y, that's either -1 or 1. Those are classes. And I have predictor variables x. And the support vector machine problem looks as follows. I'm going to fit beta and beta naught. That's like an intercept term, and then beta determines a hyperplane. And these psi variables are my slack variables here. And this is a QP, right? And it looks like minimize 1/2 times the norm of beta squared. That's the size of the margin in the support vector machine, plus c times the sum of the psi i's. That's kind of like a penalty we incur for putting things in the points on the wrong side of the margin, subject to the following constraints: psi is bigger than or equal to 0, and we get that yi transpose yi times the quantity xi transpose beta plus beta naught is bigger than or equal to 1 minus psi I. So let's just go ahead and drive its dual. It looks like we're going to write down the constraint says, so minimize I'm going to write this constraint as psi is less than equal, minus psi is less than equal to 0. I'll call these v. And I'm going to write this as 1 minus psi I minus yi times xi transpose beta plus beta naught is less than equal to 0. And I'll introduce two variables here, ui. Or, sorry, I guess I called it w in this case. wi, and these are all non-negative. And so the Lagrangian, right, is L of x v w, which is just this. And we have minus the sum of vi psi I plus the sum of wi times the quantity 1 minus psi I minus yi transpose y times xi transpose beta plus beta naught. Okay, now let's minimize that over the primal variables. I call them x here, but really what's the set of primal variables? It's beta, beta naught, and psi. So let's group these terms accordingly. What do all the terms involving beta look like first? Let's just write those down. I have that minus the sum of wi times yi times xi transpose beta. What is that as a function of beta, which is a quadratic? Let's write down the terms involving beta naught. I just get minus wi times yi times beta naught. And let's write down the terms involving psi. I get the sum of c minus vi minus wi times psi I. And then I have left over, I just have the sum of the wi's. I didn't account for yet. Okay, so let's minimize this over beta, beta naught, and psi. Let's do some of the easy ones first. What happens if I minimize over beta naught? I get minus infinity unless this term's 0. Otherwise, there's no constraints on beta naught. I just take that beta naught bigger and bigger in the right direction as long as that term's 0. So minimizing over beta naught, we get that wi must be 0. And when that's the case, we don't get any contribution. It's just that part's just 0. How about minimizing over the psi i's? I get that for the same reason, right? Each of these terms must be equal to 0. How about minimizing over beta? What do I get? Well, I'm going to write this as 1/2 beta transpose beta minus w times w transpose x tilde times beta. X tilde is the matrix x, but where I've multiplied each row by yi. I just alter the sign of each row by multiplying it by yi. Just for notation, it's cleaner to write it that way. Then this term becomes w transpose x tilde, the matrix x tilde times beta. So how do I minimize that over beta? What's the minimizer? Right? It's just going to be equal to x tilde transpose w minus b over 2a. A is identity matrix. It's a half in front. And so when I plug it in, I'm going to get the the term minus 1/2 W transpose X tilde transpose X tilde times beta. No. Yeah, that's right. Sorry. Okay. All right, so now we've formed the dual. I've just written it differently on the slides in matrix notation, or in matrix vector notation, right? That's the contribution from minimizing beta. The 1 transpose W, which is the sum of W's, is left over. When I minimize over beta naught and psi I, both these terms are 0, subject to the constraints that I've written down here. So that's the Lagrange dual function. It's a function of V and W. And therefore, the SVM dual problem becomes maximizing this function over all dual variables W and V, subject to these constraints. And all I've done is I've eliminated the slack variable V. You can see here that V is a slack variable, right? Because all it appears is in this constraint, nowhere else. So we say that this says that Wi has to equal C minus Vi for all I, but it doesn't appear anywhere else. And Vi we know has to be bigger than or equal to 0, so these two together I can write as Wi is less than or equal to C, and just get rid of V as a slack variable. So I've done that, and then just written down the problem here. This is the SVM dual that you know and love from a previous class. So Slater's condition is satisfied, right? Why is that true? Because, well, actually there are no constraints here that are not linear, so all we have to do is make sure there's a feasible X. That's a feasible W. That's certainly going to be true, right? Some W between 0 and C, such that W transpose Y is 0. That'll be true if C is big enough. In fact, that'll always be true, right? Even if C is small, as long as C is bigger than or equal to 0. W is 0 is feasible. All zeros. So Slater's condition is satisfied. Therefore, we have strong duality, which means that if we were to solve this problem and solve the SVM problem, then we get that their criterion values are equal. That's almost very useful. We haven't quite seen the full use of duality yet. Here's why duality is so useful. Because not only do we get equality of the criterion values under strong duality we very often get a fruitful relationship between the primal and the dual solutions. That's really what we care about. For SVMs, if you guys have studied that in a previous class, you might recall that if we had the dual solution W, we could get back the primal solution we care about, which is beta, determines the hyperplane, by multiplying X tilde transpose by W. That's the relationship in the primal and dual variables. Where does that come from? Actually, you can think about it comes from the minimization of the Lagrangian, right? Just from this step, the minimizer was beta, which is equal to X tilde transpose W. That tells us the relationship between the primal and the dual variables. Just the minimization of the Lagrangian. We'll see this more formally next time when we study the KKT conditions and we actually have more general rules for relating primal and dual solutions. But this is one of the driving uses of duality. If the dual problem is easier to solve, and we have strong duality, then we can get actually a primal solution very often from a dual solution. Questions about this SVM example, or just anything? Yeah?
Do we check the Slater condition in primal or in dual?
In the primal. Yeah, the Slater condition is a condition on the primal. But if you remember the LP problem, we applied the Slater condition to the dual, and it told us something about its dual, which was the primal. So I suppose, it can be useful in some cases to check it on either problem. If you know the dual is the primal. But the simplest answer is that for strong duality, you want to check Slater's condition on the primal. Other questions? Okay, here are two uses of duality. I'm going to go through them really quickly because I actually want to get to this matrix games example, which is pretty interesting. And we'll come back to these when we talk about uses of duality for a whole lecture, not next time, but the time after. Two uses of duality are, one of them is the duality gap. So if you ever had a primal feasible x and a dual feasible u and v, we know that, first of all, f of x minus g of uv is bigger than or equal to 0. That we know for sure. Furthermore, we actually know that the distance between f and f star at x is no larger than the distance between f of x and g of uv. I'm saying distance, I really just mean the difference. Why is that true? It's because this member provides a lower bound. GUV lower bounds f star for all dual feasible u and v. So minus GUV upper bounds minus f star. That's where this comes from. So suppose we were performing some iterative minimization where we first took a step on the primal, then we took a step on the dual, and we were kind of solving them at the same time just because we wanted to. Then at any point, we could check the dual criterion, check the primal criterion, take their difference. That would upper bound how far we are from optimality in the primal. It's extremely useful. We actually so far have had no way of doing that so far. Right? Our stopping rules have been things like stop when the gradient's small if we're doing gradient descent, stop when the change in criterion is not very much over iterations, stuff like that. This gives us a much more rigorous stopping rule. It tells us precisely if we stop when the duality gap is less than or equal to epsilon, we are no more than epsilon from optimality. Here's, this is not a use of duality, this is just kind of a correspondence of duality. The second use of duality was this one, finding primal solutions from dual solutions, which we'll talk about, like I said, in coming lectures. Dual norms are also something that we kind of get out of our understanding of duality. You've seen this, I think, we've hinted at this before. Basically, for any norm, there's a corresponding dual norm. And it's defined as follows. The dual norm of x is equal to the maximum over all points z, whose norm is less than or equal to 1, of z transpose x. And we get a bunch of very useful kind of properties out of the dual norm. I'm going to just leave this until next time because we'll go over it in detail. Another dual correspondence. So let's jump right to this example that I wasn't able to cover last time. And then we'll finish. Here it is. Okay, so suppose I'm playing a matrix game with someone, and we have two players, call them J and R. And these two players are going to play the following game. J is going to choose some quantity I from 1 through m. R is going to choose some quantity little j from 1 through n. And then we're going to go to this lookup table. It's called our payout table. And J is going to pay our Pij. Okay, so don't feel too bad for this player J because this can be positive or negative, right? So it's not like R is always going to come out on top. It's just the payout is just a real number, positive or negative. And J and R are going to each use mixed strategies. So J is going to choose I randomly, uniformly at random. Actually, sorry, not uniformly at random, but he's going to choose it randomly according to some probability distribution x, so that xi is the probability with which he chooses I. And R is going to lay down a probability distribution, and he's going to choose J with probability Yj. And now we're going to think about how the two players might choose these probability distributions x and y, which determine their strategy. So first of all, let's compute the expected payout if J was using strategy x and R was using strategy y, and the payout matrix was P. Then it would just be the sum over all I and j of xi, yj times pij, or written more concisely, it's x transpose py. That's the expected payout from j to r. Let's suppose that player j was wiser, and he decided that he was going to let r know his strategy ahead of time. So he's going to actually tell r, I'm going to use strategy x. What would r do in that case? Well, he would choose y in order to maximize his expected payout, right? There's nothing else that would make sense. If he knows the strategy of his opponent, choose your strategy to make the expected payout the largest. So he'd think about, how can I choose y so that x transpose py is largest? Y has to be a probability distribution, so it has to be non-negative and has to sum up to 1 across all the options. This ends up just being place essentially all of the weight on the largest component of P transpose X. Okay, if you were to work out that calculation, that's what it ends up being. So what's J's best strategy then? Since he's wise, he knows that if he gives R his strategy, then R is going to try to maximize his expected payout. So J is going to choose Y to minimize his whatever he ends up paying out, according to what R would do. And then he'd give that to R, and R would choose what he thinks is the most favorable strategy, and J would suffer in a sense the worst loss under that. Sorry, the least harsh loss under that scenario. All right, so he's going to choose his strategy X to minimize whatever the payout is going to be if you were to tell that strategy to R. So he basically forms this problem: minimize over all X, the maximum from I going from 1 through n of P transpose X in the ith component, subject again to X being a probability distribution. This is called a minimax strategy, right? Choosing it so that you're protecting yourself against the worst case. All right, that's a convex optimization problem, by the way, right? For a given payout matrix P, we could write this down and solve it. In fact, it's just a linear program. We can transform it into a linear program. So if in some bizarre alternate universe, R was wiser than J, we might flip the situation, right? We might say that R would give his strategy to J beforehand, and then J would try to maximize his expected payout, and R would try to protect himself against the worst case. That's also something that may happen. Think about what would happen then. Well, you could see that then R's best strategy would be to choose the distribution y according to the following program: maximize overall y, the minimum overall j going from 1 through n of the biggest of py in the jth component, subject to y being a probability distribution. The reason that these are flipped is because, remember, the payout can be positive or negative. That's the only reason why. So, if you thought about this for a few minutes, you would see that this argument came from this problem came from the same argument as the one we just gave, just in reverse. All right, so now clearly it is favorable, right, to know an opponent's strategy. That has to be intuitively true. And we're talking about payouts from J to R. Right? What is the payout that R will receive at the end of this game? So let's call F1 star the payout that R receives when he knows J's strategy, and F2 star the payout he'll receive when he doesn't know J's strategy. In fact, when J knows his strategy. So the situation is completely reversed. Then it's kind of intuitively obvious, right, that F1 star is going to be bigger than or equal to F2 star. The payout has to be bigger when R knows J's strategy than if he didn't, and if the reverse were true. There's a very kind of famous result called von Neumann's minimax theorem. It tells us that actually in this situation, F1 star and F2 star are equal. It's pretty amazing. This, in a sense, marked the birth of duality for linear programs. And I guess we're a little short on time now. The proof is actually not very hard at all, now that we know Lagrange duality in its latest condition. Essentially, we're just going to recast the first problem as an LP. So remember, the first problem looked like this. Minimize the maximum value of P transpose X in the ith component. Overall, I going from 1 through n, subject to the following simplex constraints on X. Write that as an LP by introducing a variable t and saying that we're going to minimize the value of t subject to the simplex constraints on X, and P transpose X has to be less than or equal to t in every component. Right? Whatever the smallest t that makes this true, the value of this linear program will be equal to the value of the optimization problem we just wrote down. It's just a reparameterization. Now let's form the Lagrangian for it, right? we could have done this in one of two ways, actually. We could have also used the original construction for LP duals that we learned before, but it's just as easy to do it with the Lagrangian. And the Lagrangian is a function of the primal variables, x and t, and three dual variables, one that I introduced for each of these constraints, u, v, and y for this constraint. So if you write it down and you form the Lagrangian, you'd see that because it's linear, right, we have to introduce equality constraints, otherwise the Lagrange dual function can be negative. We can minimize it without end. And you'll see that the minimum ends up just looking like v subject to the following constraints on the dual variables. Going through that exercise, you get to the following dual problem. Maximize overall v, subject to simplex constraints on y, and the constraint that py of x has to be, p times y has to be bigger than or equal to v in every component. What is this problem, the dual problem? It's exactly equal to the second problem that we were considering. So the dual of the LP in which R knows J strategy is the problem in which J knows R strategy. Those two are duals of each other. So by weak duality, of course we know that the primal optimal value has to be bigger than or equal to the dual optimal value. But here's where strong duality comes in. Strong duality holds because we're in a linear program setting. You can check that Slater's condition is satisfied, or you can just tell yourself that if P is not a crazy matrix, let's say this problem is feasible. Right? So let's just say for a not crazy payout matrix, this is going to be a feasible linear program. Therefore, Slater's condition is going to hold, and we'll get strong duality. That may seem somewhat abstract in the LP sense, but it's actually something very interesting and very surprising here. Has kind of a game theoretic implication, which is that it doesn't really matter who knows whose strategy. Expected payouts are going to be the same in either case. So this I think was a very important result in LP duality, and also it spawned a bunch of work in these kind of minimax games as well. Questions about that result? Yeah.
For what class of problems does this maximum important?
Do you mean if I wasn't using like a linear payout scheme? So I would give you a cheap answer and say that if you can formulate it as a convex problem and the converse problem as its dual, then it holds under strong duality. I think that somebody who knows more game theory than me would certainly know a better answer than that. Do you know the answer to that question?
So if you talk by linear term, so if you have the min max over compact sets, you could flip max and min match. So in this case, you could rewrite this as min max, and then you have x transpose py as the function. If you have that same thing that the min and max are not over sequences as here, but over compact sets.
Right. All right, we'll see you on Monday. We'll talk about the KKT conditions then.